here is the flux divergence version of Green's theorem. And so on the left here is just the flux, and the right here is integrating the divergence. So let's apply the flux divergence version of Green's theorem to calculate flux of F is equal to x cubed, comma y cubed plus y out of the unit circle. So unit circle here, this is our C. And so once again, and just like in the previous video, instead of calculating out the flux integral on the left, we're going to choose to compute a double integral of the divergence over, in this case, the unit circle, the interior of the unit circle here. So in order to do this, we need the divergence of F. The divergence of F is we take the partial derivative, this is the equivalent, I should just say here, to partial derivative m with respect to x plus a partial derivative n with respect to y. It's the partial derivative of this respect to x plus the partial derivative of this respect to y. Partial derivative of this respect to x is 3x squared. The partial derivative of this with respect to y is 3y squared plus 1. So we need to be integrating 3x squared plus 3y squared plus 1 on, let me call this here R. R is the region inside the unit circle. So the flux is equal to the double integral over R of 3x squared plus 3y squared plus 1 dA over the interior of the unit circle here. How do we do this? This is going to be most easily done in polar coordinates. So we have to do set up and evaluate this integral in polar coordinates. So this is unit circle here. Everything inside the unit circle. So theta will run from 0 to 2 pi. And R will run from 0 to 1, radius 1 here. 3 times x squared plus 3 times y squared, that's 3 times r squared plus 1 r dr d theta. And so this is a straightforward enough integral to evaluate. We can separate this out. Theta from 0 to pi d theta times integral r from 0 to 1 of 3r cubed plus r dr. This first integral is, of course, 2 pi. The second integral, this will be r to the fourth. This would be r to the fourth, 3r to the fourth over 4 plus r squared over 2. Where r goes from 0 to 1. So 2 pi times 3/4 plus 1/2, or 5 pi over 2 as our final answer. And so again, this is a pretty easy way to compute things. What does Green's theorem allow us to do in general? It allows us to replace calculating vector line integrals with double integrals over regions in the plane. And so it changes problems from like section 16.2 to problems from chapter 15 in this very useful way.